There are many applications of integration to physics. Work is one of them. Work is force times distance. We're going to look in particular at moments and centers of mass. So I have here a little example. We've got a little balance scale. 10 centimeters from the center, we have a 15-gram mass that we're going to suspend. So let's suppose that we have a 30-gram mass, one that's twice as heavy or as massive as the 15-gram mass. Where should we hang it so it balances perfectly? Well, it's pretty clear that if I put it at the other end, 10 centimeters away from the fulcrum, down here, the fulcrum being the little piece in the middle, that it's going to lean towards the left, like so. We don't want that to happen. So what that means is we're going to have to actually sit a little bit closer to the center in order for it to balance. How much closer to the center should we sit? If you're having trouble picturing this, imagine a child and their parents sitting on a teeter-totter or a seesaw, whatever you want to call it. When the child is at one end and the heavier parent is on the other side, they have to sit closer. Again, how much closer? Intuition would make you think, well, if we sit half the distance, here is our 30-gram mass, and we're going 5 centimeters away. If we sit like that, then it would seem like it should balance. And that is actually correct. Now, I want to make this little observation for us here. Take the mass, 30 grams, and multiply it by the distance. If we do that, we end up with 30 times 5. On the other side, if we do the same thing, we would have 15 times 10, both of which equal a common value of 150. So the system will be in balance if those two products are the same. Let's see how we will go about figuring this out in general. Okay, suppose I have two masses, mass M1 over here and mass M2 back here. M1 is at position X1, M2 is at position X2. And suppose the balancing point here we call X bar. In math, when you see a bar over top of something, it's often something of some sort of average. We'll see an example of an average that may not feel like this, but is precisely this kind of idea in just a moment. The question is, how do we figure out what X bar is? Here's the way we develop the formula, and then this will generalize if we add more masses in more places. This distance, we've got to be careful, is going to be X sub 1 minus X bar. This distance is the reverse, X bar minus X2. Now we'll do a little calculation over here. We said that the distance between them multiplied by the mass should be equal when we do this. So that means that X bar minus X2 multiplied by M2 should be equal to, the other distance was X1 minus X bar. We multiply that by M1. And our quest is to figure out what X bar is equal to. A little bit of algebra gets us there. We distribute the M2 through. We collect the X bars on one side of the equation. I'll do this on the left side. Factor out X bar and divide by the sum of M1 and M2. And our final value for X bar is X1 times M1 plus X2 times M2 divided by the sum of M1 and M2. The value in the numerator, each of these represent what we call the moments of those particular masses. So we have two moments here. The sum of those two is the moment of the system, and then the sum in the denominator is the mass of the system. And this generalizes nicely. We're going to do kind of it seems like it doesn't apply, but it actually does. In a class, 15 of 100 points are your final grade, 65 is for quizzes, and 20 is for the final exam. A student earns 95% on the homework, 80% on the quizzes, and 85% on the final. What's their final grade? Well, students are often familiar with these weighted averages. So we got a 95 on the homework, which is worth 15 points. So that would be 0.95 multiplied by 15. And then we got, let's see, an 80% on the quizzes. So that's 0.80 multiplied by the 65. And then we got an 85% on the final. Well, that's 85 out of the 20. This turns out to be, well, wait a minute. We don't want to do that quite like that. Because what we're doing here is we've got the 100 points. We want to know our average. All of our averages have been represented by decimals, 0.95, 0.80, 0.85. So in order to make this a decimal, we would want to divide by, so we're going to add a division bar, the total number of points, right? Which would be out of 100. So it should be 83.25%, but as a decimal, it's 0.8325. And so now you're saying, well, what's the connection here? What we can imagine is that we have at position 0.95 a mass of 15. And at 0.80, we have a mass of 65. And at 0.85, we have a mass of 20. The total mass is 15 plus 65 plus 20, which is 100. Where does it balance? It balances at our average grade. And so that's kind of what we've done here. So we now have masses, particles with masses m1 through m sub n at the points x1 through m sub n. The center of mass of the system is the sum of those moments of the individual masses divided by m, where m is the total mass of the system. Again, each of these products, m1, x1, m2, x2, each of those is called a moment of that particular mass. And then the sum, the total value in the numerator is the moment of the system about the origin. Okay? Origin, 0. Okay, so we have masses of objects of mass 2, 3, 4, easy to remember, are at positions -2, 5, and 7 respectively. We want the center of mass. Well, in the denominator, we want the total mass of the system. That would be 2 plus 3 plus 4. So that's going to be 9 in the end, I know. And we want the moments of each individual mass. So the mass 2 is at position -2. So its moment is 2 multiplied by -2. And then mass 3 is at position 5, so it would be 3 times 5. And then the mass 4 is at position 7. And so the center of mass is at 39/9. Just a little bit, well, I guess that reduces a little bit, does not reduces to 13/3. So just a little bit bigger than 4. And that kind of makes sense because the heavier masses are at positions 5 and 7. 2 is the lighter one and it's at 2. So you would think kind of close to 4-ish because that's near where those larger masses are placed. Well, this extends if we want to start plotting points all over the place. And when we plot those points, we place masses at those points. We can find this moments and centers of mass here as well by doing something similar. The moment about the y-axis, oh, this is really weird. The moment about the y-axis, we're going to take the mass multiplied by the x value. Why is that? We'll figure that out in a moment. The moment about the y-axis, we take the product of the masses and the x values. The moment about the x-axis, we take the product of the masses and the y values. The center of mass, we just kind of do what we did in the previous example, but we take the individual moments and divide by the masses. This is strange. The moment about the balancing point in the x direction is the moment about the y-axis divided by m. Now I can understand why it would be my, since my has the collection of x's, but why do we call that the moment about the y-axis? The reason we do that is because when we are moving left and right, we would think about balancing points being sort of like a vertical line placed maybe at the y-axis so that it balances left to right. That's why it's called the moment about the y-axis. Okay, so we have a new problem here. Objects of mass 6, 2, and 5 are placed at these particular points. So let's plot these points, label each point with their mass, and then figure out where the center of mass is going to be. So I've gone ahead and I plotted each of these points and wrote the mass of the object at those points. Now, of course, these points create for us a little triangle. And so the balancing point, that's really what we're looking for. The balancing point would be a point where it's actually going to lie on the interior of this triangle. Where? I don't know. Well, I would think it would be closer to the 6 and the 5 because 2 is not a very heavy balancing point. It's not influencing the weight too much. So I'm going to guess that it's somewhere in this region, maybe a little bit closer to the 6 there. We need to figure out the moment about the y-axis, the moment about the x-axis, and the total mass of the system. The moment about the y-axis, remember, is the product of each mass and the x-coordinate of the point. So 6 is placed at 1, 2. We're going to multiply that by 1. The object of mass 2 is placed at position -3. And the object of mass 5 is placed at -2. If you're playing along, you've probably calculated that that's -10 already. The moment about the x-axis, on the other hand, we're going to take each of these masses and multiply them by the y values. Again, that's strange. The moment about the x-axis, we're multiplying by the y values, but that's the way it works. So 6 times the y value of the first point is 2, plus 2 times the y value of the second point is 4, plus 5 times the y value of the last point, which is 0. And so we end up with 20. We also need the total mass of the system. Now, it's not listed here, but it's the same as we had before. The total mass of the system is just the 6 plus the 2 plus the 5, which is 13. That means that x bar, the x-coordinate of the center of mass, is going to be my divided by 13. So that's -10/13. Y bar, on the other hand, is mx divided by 13, which is 20/13. If we plot this, the first point is not quite -1, and the second point is about 1.5. So let's see where that would be. It's -1, not quite -1, and about 1.5, somewhere in there, in that region. That's the balancing point. And again, it kind of makes sense. It should be closer to the masses of the objects of mass 6 and 5 because they're heavier. And I would think it might be slightly closer to a one of mass 6. Our ultimate goal here is to take regions in the plane, maybe triangles, but triangles are kind of boring, but we'll take other regions in the planes, things that have curves to them, and they're solid, they're uniform density in that region, and we want to know the center of mass there. Okay, so here is our goal. I have here just a region. Don't worry about this stuff just yet. It's a little bit intimidating, but it's not too bad. We have some sort of region in here, and we want to know where its balancing point is. The idea for finding the balancing point is to find a left to right balancing point, so maybe right in there. And then find the top to bottom balancing point, maybe right around in here. I could be wrong. The intersection of those two, the vertical line there and the horizontal line, the intersection will be the balancing point of the system. So we've got to find that. In order to do that, one of the things that we'll need for both the left to right balancing point and the top to bottom balancing point is we need the mass of the system. Now, the mass is actually not a terrible thing to calculate. To get the mass, we're going to do as we've been doing. We're going to take just one little rectangle and think about the mass of that rectangle. Now let's go up to the stuff that's up here. We have a flat plate. So this is our flat plate here, the pink region, of uniform density. Density is often measured in some sort of unit of mass per unit of area. So grams per square centimeter, that sort of thing. That's what the density is. Well, in order to get the mass, think about the density. It's unit of mass per square something. So if I know what the density is, we're going to call it rho. If I want to know what the mass of this particular rectangle is, I'm going to want to multiply that density by the area. So we're going to take rho multiplied by the area. Well, the area we should know. Let's call that again dx, kind of hand wavy. If this is the function y equals f of x, the area of that rectangle is going to be the function, the height of the rectangle, multiplied by the width. So f of x dx. So the area of this particular, the mass of the system is just going to be the area. This is the mass. Multiply, the mass is the area multiplied by the density. That's what m is equal to. Well, the area is just the integral from a to b f of x dx. So that explains sort of this formula here. The mass is that. Okay? Now, we're going to deal with this whole x bar, y bar stuff in a moment. Don't worry about that. Now let's talk about the moments about the y-axis and the moment about the x-axis. I'm actually going to do the moment about the x-axis first because it's a little bit easier to handle. Now let's look back at our rectangle. Where would this rectangle balance? Well, rectangles are beautifully symmetric. It's going to balance right there, smack dab in the middle. So what we could do is we could take that entire rectangle and replace it by that single point to represent its mass, or to represent its position and mass. The balancing point is actually at position, well, let's see here. If on the curve, if that's x comma y, the balancing point is going to be at x comma 1/2 of y. But y is f of x. So the balancing point, remember we did this little business where we took the sum of the masses multiplied by the y values? Okay, our y value is 1/2 times the function value. So the moment about the x-axis, we're going to take the area, or the integral from a to b. We're going to multiply the mass. Well, the mass is just what we did before. It's rho times f of x. And we're going to multiply that by the balancing point. And we said we could treat the balancing point here as the representative for the entire system. So we're going to have 1/2 times y, but y is f of x. And when we simplify that, we can pull the row out front. And we have the integral, we want the integral from a to b, and we still have 1/2. We've got two factors of the function value, and that's going to be squared. Okay, so that's where this particular formula comes from. And now we want the moment about the y-axis. The moment about the y-axis, well, that's going to be a little bit trickier. Well, we want the position. Well, the position actually is pretty straightforward, isn't it? If we say that this point, x comma 1/2 y, represents the balancing point for this, then the position left to right, since we start at 0 and we end at x, the position is just x. The mass is the same thing as it was before, so we're going to do the integral from a to b. The mass is rho times f of x. The position we said was just x, and so we can pull that row out front, integral from a to b, x f of x dx. So that's where these formulas come from. And so now let's explain the x bar. I'm just going to do x bar, not worry about the y bar because it's similar. X bar would be the moment about the y-axis divided by the mass of the system. Well, the moment about the y-axis is rho times the integral from a to b of x f of x dx divided by rho times the integral from a to b of f of x dx. Those rho's will reduce. Rho divided by rho is 1. And then the denominator is just the area bounded by the curve in the x-axis. And so this becomes 1, not plus, equals 1 divided by the area multiplied by the integral from a to b of x f of x dx. So in the long run, that rho has no effect on things. And notice that we ended up with the same thing that's here. So if we're only asked for the center of mass, we really don't need to worry about this rho business and that sort of thing. If I'm asked for the moments, I need to be given rho, or I can just assume it's going to be some uniform density rho. So here is our first example. We want the center of mass of the region bounded by that curve and the x-axis when x is between 0 and 4. Okay, so let's plot some points here. Here is the graph of y equals x radical x. Since I don't have to find the moments, I don't need to worry about the density and that sort of thing. So what I need to know is I need to know the area, and the area is simply the integral from 0 to 4 of x radical x dx. Now, of course, we can't evaluate it that way. We've got to treat it as x to the 3/2 dx. And this turns out to be 64/5. If you need to, pause it and review what I've done here. Now we're going to calculate x bar. As we saw in the previous slide, x bar is 1 divided by the area multiplied by the integral from, in our case, 0 to 4. And now we have to think about what this is. Well, again, this is why I like to have the picture. The x bar is sort of a left to right kind of business, is it not? It's the left to right kind of business. And when we want to find the balancing point, that was when we took x and multiplied it by our function. Our function, so it's going to be 1 divided by 64/5 times the integral from 0 to 4, x times x radical x dx. And you can take the reciprocal, that's 5/64, multiplied by the integral from 0 to 4, and this is going to be x to the 5/2 dx. Which, when you can compute it, is 20/7. Again, pause if you need to. Now we do y bar. Y bar is 1 divided by the area, integral from 0 to 4, and then we do 1/2 of the function value squared dx. Okay, and remember the 1/2 goes with one of those factors of f of x. 1/2 f of x is the halfway point up and down that rectangle. That's what helps me remember this. And so this is going to be, we'll go ahead and do the 1 divided by 64/5 and write that as 5/64 times the integral from 0 to 4. We're going to do 1/2, and then we square, oh my goodness, we square the x to the, oh nice, x to the 3/2 dx, because that's what our function is. Our function is really x to the 3/2. I'm going to pull the 1/2 out with the 5/64, so that becomes 5/128. And we're looking at the integral from 0 to 4 of x cubed dx, a nicer one. And so we get 5/128 multiplied by 1/4 of 4 to the excuse me, not 4, I'm jumping the gun here, of x to the 4th, evaluated from 0 to 4. And this equals 5 halves. So if we plot our point, 20/7 is just a little bit shy of 3. 21/7 would be 3. 5 halves is 2.5. So if we go to the point just a little bit less than 3 and 2.5, that's supposed to be our balancing point. And I can believe it. It should be more towards the right because that's where it's taller. And we should kind of have to balance out the 3 corners of the triangle. Well, it's not quite a triangle, but it looks triangular-ish. For our last example, we actually are going to calculate the moments and the center of mass for the region bounded by e to the x, both the x and y axis, and that line x equals 2. We're assuming that the uniform density is rho equals 5. So we're going to throw in the density in this particular problem. Here is the graph of the region. And so first of all, we'll calculate the mass of the system. The mass, remember, is the rho times the area. Our rho is 5, so it's going to be 5 times the integral from 0 to 2. The area is just e to the x dx. This is going to be 5. The antiderivative is e to the x, evaluated from 0 to 2. Be very careful. When x is 0, we do not get zeros this time. It's 5e squared minus 5e to the 0th, which is just 5e squared minus 1. The moment about doesn't matter which we do, I'll do the y-axis first. It's going to be rho multiplied by the integral from 0 to 2. And the moment about the y-axis, this is the one where we're moving left to right. When we're moving left to right, we incorporate the x in there. So it's x times my function dx. Oh, I know what's going to happen here. Our rho is 5. We're going to do from 0 to 2. X times e to the x dx. This is going to require integration by parts. If the x weren't there, we could evaluate the integral with no problem. So we want to get rid of the x. That means our choice of u is going to be x to get rid of it. dv is e to the x dx. Ran out of room there. V will be e to the x, and du will simply be dx. So we end up with 5. That 5's got to go to both these, doesn't it? U times v is x e to the x, evaluated from 0 to 2, minus the integral from 0 to 2 of v times du. Well, that's just e to the x dx. When x is 2, we end up with 5 times the quantity of 2e squared. Now this time, because of the x in front of the e to the x, when x is 0, we do get 0. So I'll just leave that alone at this point. And then we'll have minus the antiderivative of e to the x is e to the x, evaluated from 0 to 2. And in the end, we end up with 5 times the quantity of e squared plus 1. For the moment about the x-axis, we use the formula again. It is rho multiplied by the integral from 0 to 2. We take half of the function value squared dx. I'm going to pull the 1/2 out front with the rho. Our rho is 5. We're going to pull the 1/2 out with it, so 5 halves times the integral from 0 to 2, and we're going to square e to the x. Okay, I suggest that you pause for a moment and puzzle out how you evaluate this integral. The way we evaluate it is we're going to use the property of exponents. We're going to take 5 halves, multiply, or we're going to look at the integral from 0 to 2. We will multiply the x and the 2, e to the 2x dx. The antiderivative of that will end up still with the 5 halves out front. The antiderivative is e to the 2x But because the exponent is linear and its derivative is 2, we have to multiply by 1/2 to compensate for the 2 that would be produced through the chain rule in checking our work. Evaluating this from 0 to 2, again, be careful. When x is 0, we do not get 0. And we end up with 5/4 multiplying the 5/2 by 1/2. When x is 2, we'll get 2 times 2 as the exponent. So we'll get e to the 2 times 2 is 4, minus then 5/4 of e to the 0th. And I'll pull out the 5/4. That's 5/4 of e to the 4th minus 1. And so now the final step, since we want the, so we have the moments, we want the center of mass, we need to know what x bar and y bar are. X bar was my divided by m. M sub y was, where is it? It's 5 times the quantity of e squared plus 1. And that's divided by, and I've made a mistake up here, I've just caught it here, the 5e squared minus 1 up here, that should be 5e squared minus 5. So let me fix that. And at the same time, I'm going to go ahead and say, well, let's factor out the 5. 5 times e squared minus 1. So we would have 5 times e squared minus 1, which reduces to e squared plus 1 divided by e squared minus 1. On the other hand, y bar was m sub x divided by m, the mass of the system, which is equal to m sub x, we said was 5/4 of e to the 4th minus 1 divided by 5 times e squared minus 1. And the 5 and the 5/4 and the 5 in the denominator will reduce, and this actually reduces to e to the 4th minus 1, and then divided by 4, that 4 coming from the 4th in the numerator, times e squared minus 1. There's a little more simplification you can do in that particular one. The e to the 4th minus 1 will factor if you want to go ahead and play with that. Also, if you want to, hang out for just a second here, and I want to show you a connection between the two formulas and something else that is very familiar to us. All right, thank you for hanging out. Let's look at m sub x and m sub y. M sub x, remember, was rho times the integral from a to b of 1/2 of f of x quantity squared dx. And m sub y, I'm going to leave a little bit of space here, was rho multiplied by the integral from a to b of x times f of x dx. Now I want to show you a connection here. Let's suppose, and for no good reason other than to make a point, let's suppose that rho is equal to 2 pi. Some people like to refer to this number as tau, and they even get into kind of strange battles. If we do that, the first one becomes rho multiply, I'm sorry, not rho anymore. Rho is now 2 pi times the integral from a to b of 1/2 of f of x quantity squared dx. The 2 and the 1/2 will cancel, and so this ends up being pi times the integral from a to b of f of x quantity squared dx. A rather messy one there, but that's what it is. That should look familiar. That quantity is precisely the formula that we use when we're trying to find the volume of a solid when it's revolved about the x-axis. Interesting. Let's see what happens in the second one. We said rho is equal to 2 pi. So 2 pi multiplied by the integral from a to b of x times f of x dx. No simplification needed here. This formula is precisely the formula that we use when we're trying to find the volume of a solid when it's revolved about the y-axis. So there is this connection that you can make between these moments and centers of mass and the volume problems that you have done previously to this.